Welcome back. In this lecture, we are going to talk about work and heat. Now, some aspect of that was covered in the first week of the lecture, this course, but using a different set of postulates. What we are going to do is we will try to little bit change the way we have treated here to provide more comprehensive illustration of the thoughts on how the work and heat concept was originated. Now, so in this particular lecture, what we want to do is we want to establish the relation between work, heat and energy. So, that would of course will lead to the first law or the conservation of energy. But this has been the key focus for modern thermodynamics, mainly by many scientists, Sadi Conard, James Joule and Lord Kelvin. So, what we are going to do is we are going to just define first basic definition of mechanical work. So, a work interaction between two systems which occurs when their boundary moves under any action of the force F. So, this is what we all know, that there will be a work interaction between the two systems when their boundary moves under a force F. So, this is a basic definition of mechanical work. So, for the case of one dimensional displacement over a differential distance, okay, the amount of work is quantified as this, del W is equal to F time dx. Okay. So, the total amount of work between two specified position essentially is going to be integral of this. The reason why putting delta here is that the force, or in general the total amount of work, depends on the path along which the process has occurred. Thus, the amount of work is an inexact differential, and thus we represent it by delta. Okay. So, for the case of finite displacement, we just simply take the integration of F. So, what is F here? F is nothing but the resultant force acting on the subsurface or boundary of a rigid body at a point when there is a differential displacement of the boundary. Now, here Fs is written here. Fs is basically distinguished from the body forces or forces associated with an external field, such as gravitational, centrifugal, inertial, coulombic, etc. So, for such one we will be going to write it separately. If they are Fb, that means the body forces are there, then we are going to add it up, or you make use of a Newton's second law, and we are going to add all the forces, okay, acting on the rigid body. Okay. So, this is what we know. This is the basic mechanics which we are well aware of. Okay. Now, let us make use of this understanding and consider a weight which is suspended by a string, and the free body diagram is given here. So, you have a hook, you have a string, and the force here is Fs, and this is the body force. So, this is basically gravitational force, which is mg, and if it is moving, then basically we are saying mg minus ma. So, this assuming this is basically collinear, that means the Fs and Fg is collinear, okay, then we can consider for the case of if the object or the body is not moving, then essentially you have the scenario, okay, which is Fs plus Fb or Fs minus mg is equal to 0. If Fs is increased slightly, then the weight will rise. If it is moving, then essentially you will consider the movement in the form of acceleration ma, or this particular force. So, Fs minus mg minus Fa is going to be 0. Okay. So, this is a basic mechanics here. Now, the corresponding differential work which will be done on weight is going to be the Fs multiplied by dx. So, this is the weight, this is basically the differential work done on the weight, and Fs now from here you can write it like this. Okay. So, total work on weight from position z1 to z2 would be simply the integration of this. Okay. So, that will be your mg z2 minus z1 plus m by 2 v2 square minus v1 square. Well, it is a straightforward exercise which of course we are all aware of. Now, What is interesting is we will be making use of this understanding or this basic mechanics for the case of a system which are of interest to thermodynamics. So, let us consider the extension of this for the system which is common interest in thermodynamics. So, example would be expansion of a gas. Okay. Now, this is a rigid, let us say a cylinder, you have a piston, okay, and you have a stop here. So, now consider that the pressure inside the system is more, so that it once you take off the stop is going to expand. So, the work done by the gas on the surrounding would be this will be given by delta W, that is equal to Fs, that is the force which is exerted by the gas on the boundary which is displaced, and this is you can write it as a Pg, which is again the pressure on the boundary that is displaced, okay, and multiplied by the area multiplied by the dz. Okay. So, if Fg or Pg which is at here is unknown, then we can do a simple force balance on the piston. So, this will be your Fg at the piston here minus the Pa stand for your pressure of the atmosphere, okay, minus F which is nothing but the magnitude of the friction force, which should be this, minus your the gravitational force, and then if there is acceleration of the system, that will be minus mv dv by dz. So, this is something is similar as your ma. If you rewrite in this form, then you can get this expression. Okay. Now, remember that initial force acts in the direction opposite to the motion of the motion during the acceleration. So, you can rewrite this and make use of Fg from this expression and plug in this expression, you will get this Fs ds is equal to nothing but this term. Okay. So, this will be the work done by the system on the surrounding. Okay. So, if you ignore friction, then you will have W is equal to Pa plus mg Z2 minus Z1 plus the difference in the kinetic energy. Okay. So, so this would be your kinetic energy plus potential energy, and this is the work done by the piston on the atmosphere for displacing the air and increasing the volume by dV. So, this will be your dV. Okay. So, this is a typical example of piston cylinder for the case. Now, we know that if there is a friction, there will be some dissipation. So, for the case of a system with the dissipation of friction, so the real mechanical systems are never completely free of friction, and even after well lubrication, hence usually you will see this kind of hysteresis. Okay. Even internal gradient of pressure or temperature can cause hysteresis behavior. Okay. That is something which is in the reality. Now, while we are talking about mechanical energy or mechanical work, this was thought of course much earlier by Joules and trying to particularly convert the work into heat and vice versa. So, in the case of Joules original 1845 experiments, the measurement of the change in the thermometer was one of the experiment was done. So, what they did was that slowly descended this weight, and this weight is connected to stirrer, and once it slowly descends, it rotates, leading to the increase of the temperature of the working fluid. Okay, and they found that the increase for small change in the temperature, that increase in temperature is directly proportional to the work which is being supplied to the system. So, this basic simple experiment established that the mechanical work could be converted into heat, and the conversion factor was established later as 4.18 joules per degree Celsius of temperature rise for water at the room condition. Okay. So, this illustrates the first how to convert mechanical work into heat, and that was devised in the form of, that was found in the form of temperature rise. Okay. The reverse experiment also can be considered, where basically using a fluid to produce mechanical work. Okay. So, instead of an object moving, you are trying to use a fluid to produce a mechanical work. Now, when you are doing a work on this, the temperature rises, but when the fluid does certain work, the temperature usually is going to be lower. So, production of such work will be accompanied by lowering the temperature of the fluid. The example could be something like this, where we have considered a piston of mass m confined a pure gas, let us say T0 and P0, in an insulated cylinder with a vacuum on the other side of the piston. Now, assume that the mg mass, that is weight of this piston, is less than P0 A. In other words, if you remove the stop, it is going to expand. Thus, the weight of the piston does not balance the pressure of the gas. So, remove the stop, and now what is the work interaction between the piston and gas? So, basically it does the certain work. What is the work interaction between the piston and the gas? Now, work is done on the piston by the gas. Okay, so if you ask a very simple question that what is the net amount of work needed to lift the piston, that would be very straightforward. That would be the work W here integral of F ds. So, in order to lift the weight of the piston, it will be simply the weight of this piston multiplied by delta H. So, this is the work done on the piston. But what about the amount of work performed by the gas as it expands? So, that would be W minus P dV, P times the volume change dV. Okay, so, that will be the work performed by the gas as it expands. Now, this is by definition we are putting it as a negative sign, because it is a work done by the gas, and by nomenclature we are using that to be negative. If any work done on the system, that would be positive. In general, there are many types of work interaction you can consider. So, I will come back to this example once more, but let me just summarize the typical work interaction. So, we have already talked about pressure volume. Okay, so, P dV, this is a surface deformation, okay, where sigma is basically related to stress and A is the area. Then you have this electrical charge transport, here the charge, electrical field, electrical polarizability, this is your dipole moment, magnetic polarization, frictional and stresses. So, all will have some kind of F dx relations, which would be something of these expressions. So, I am just wanted to summarize this before I go forward to the example. So, as I was mentioning here earlier, that usual convention is going to be work is positive when the done on the system and negative if done by the system. Now, let us consider the example again, where we have this here, the system with T0 P0, and now what we have done is we can replace this let us say piston. We can consider this piston which holds the sand as well. Now, we can consider this process to be extremely slow. The earlier process was irreversible, very fast. It was spontaneous because the pressure was much larger, and immediately it expands once you take it. Now, you consider this process little slow, which you can slowly remove the sand, and by slowly removing the sand, gradually it moves by lifting a pile of sand, and slowly it will come to this point. Okay, so, from T0 P0 it will change to TF PF. Okay. So, this the piston will initially accelerate upward, and later the container walls stop the piston, and final equilibrium state will be this. So, what this was our earlier example. Now, here what we have done is, now we put the sand here. Now, slowly the sand is also getting out, okay, while this process is occurring. Okay. So, what we are trying to do is that in order to maintain the same temperature and pressure as we obtain here, we at the end, when the process occurs slowly, keeping a reservoir at Tf at the end, so that the temperature is also maintained. So, the idea of this was to come up with a slow process. So, gradually removing the few grains at a time, this will allow the piston to lift slowly to the top of the container. Final temperature can be fixed at Tf by keeping a large constant volume reservoir at Tf when the piston reaches the top. Now, since it is a pure component we are considering, three variables are required for complete information. Thus, given the amount Tf and volume, the pressure would also be fixed. Now, the important thing is that what we are trying to assert here is the note that more work is performed by the piston by lifting more sides. So, the thing is that once you put this air, by the time we put this and try to maintain the temperature, some more sands are being lifted. This is compared to the other example. So, the gas has not only lifted the piston, but also lifted some sand. That is what we are trying to make a statement here. So, earlier case you were going from T0 P0 to TF PF, but here T0 PF to TF PF. In this process you have also done some other additional work while doing the process of lifting. So, your final state is still the same, but additional work is being done in this process. So, where does this additional extra work comes from? So, in order to get this point, remember that we say that we had to put some reservoir, thermal reservoir, to obtain the temperature. So, what we are saying is this must have come from heat interaction with the reservoir, okay, in order to get that final state. Thus, energy is transferred if there is a difference in the temperature between parts of a composite system. This is what we are making, because remember that the temperature here finally will not be the same. If you have just put this sand there, final temperature would be different, and that is why if you put a temperature, final temperature, if you had known that this is my final temperature as a reservoir, if we have put the final temperature reservoir, so what we are saying is that energy must be transferred, and that means the temperature was lower than TF. So, transfer of energy to the system leads to an increase in the temperature. This energy is stored in the form of kinetic energy and potential energy, which we know. Now, for classical thermodynamics, precise form of energy is not important, that we know. So, this leads to basically the equilibrium states here. So, this example which I want to talk about illustrate that basically the energy in this case is transferred, and of course, some work is being done by that particular transfer of energy, but the transfer of energy was possible because there is a difference in the temperature between the parts of the composite system. Okay. And we are setting that this would also lead to the increase in temperature. So, this was a simple example of piston and cylinder. Now, let us go to the next stage, where basically we are reasserting the equilibrium states here. Now, what we are trying to say is that in the first week of lectures we also mentioned about the equilibrium state. We are redefining this equilibrium state in the terms of different postulates. So, for the case of let us say a closed system with a given internal restraints, there exists a stable equilibrium state which can be characterized completely by two independent variable properties in addition to the masses of a particular chemical species initially charged. So, this is something which we already have talked in earlier class. Postulate 2 says that in processes for which there is no net effect on the environment, all systems, whether it is a simple or composite with given internal restraint, will change in ways as to approach one and only one stable equilibrium state for given simple subsystems. Okay. So, essentially once there is no effect on the environment for a given internal restraint, the system will approach towards an equilibrium state, and in the limiting condition the entire system is said to be at equilibrium. So, this is something which we have asserted also earlier, but I am trying to re-emphasize this, and this will lead to something called adiabatic work interaction, which becomes an interesting way to look at the conservation of energy. So, this is the case of adiabatic work interaction. So, what we are trying to do is we have considered this specifically system A and B here. So, we have a pulley, okay, attached with the weight, and there is a shaft and there is a drum. So, essentially if it rotates, so if it moves down, this will rotate the shaft, leading to essentially doing some work on this system A. So, this particular is under this particular system has adiabatic walls, and what we are trying to emphasize is something called adiabatic work interaction. So, this is an interaction involved between two closed systems for which the events occurring in both systems can be repeated in a way that the sole effect external to one system could be duplicated by the rise or fall of weights in a standard gravitational field, and the sole effect external to the other system can be duplicated by an equivalent fall or rise of weights of equal magnitude. So, if you consider this, So, what this particular statement says that the effect of this on this can be replaced by this, that the effect of this is nothing but basically this, alright. So, this is what a typical adiabatic. Why? Because there is no energy, the heat exchange here. So, adiabatic means there is insulated completely, there is no exchange of heat. So, the work whatever is done can be replaced by this aspect. So, if it is moving downward, it will move upward. Okay. Now, consider a different example where you have now system A and B, and A and B are separated by this metal partition. So, if you compare system A plus B together, okay, with system C, now this system A plus C are all adiabatic, these are all adiabatic wall, then essentially you can replace this whole system by a drum with a weight attached to it. But if you consider system A, okay, only system A, the sole effect is can be considered as a lowering of weight, because essentially this system do not change any temperature, because this is a metal partition, they essentially it will remain at 0 degree. Okay. But if you consider external B plus C here, we cannot replace system A by a drum and a weight. You can, no way you can come up with an experimental replacement of such a things. Okay. So, it is impossible to devise any experiment for which B and C's effect, sole effect will be the rise of a weight in this case. So, what it means that this tells you that adiabatic work interactions requires that all common boundaries be adiabatic wall. So, here in this case, if you consider B and C, this wall is not adiabatic, and hence we could not replace the system A by another drum and a weight scenario. Okay. So, that is a condition or conclusion based on this exercise, that adiabatic work interaction requires all common boundaries be adiabatic walls. Thus, system and boundary must be carefully delineated. Now, consider this example which you can easily solve. The situation here is below here. So, you have a generator, you have a pulley system here, and this is generator is operated by a falling weight, in which the power is generated is dissipated to a resistor. So, if you neglect any dissipative processes such as IR square, then will this be an adiabatic work interaction? And the answer is yes, you can convert this by the drum and weight scenario. So, now I move from this adiabatic work, and let us get to the energy, and then we will try to connect this adiabatic work and energy, and later to the first law. So, this is another postulate, again based, just to reiterate our understanding here. For any system 1 and 2 in which a closed system is at equilibrium, the change of the state represented by 1 to 2 and or the reverse change can occur by at least one adiabatic process, and the adiabatic work interaction between the system and its surrounding is determined uniquely by specifying the end state 1 and 2. So, what is saying is that if 1 and 2 are equilibrium states, then basically you can always connect, you can find the change by at least one of the adiabatic processes. Okay. And that adiabatic process, the corresponding work interaction will be simply determined by this end states. So, this is all summarized here, that it follows that all stable states can be breezed by adiabatic process originating from a given initial state. The adiabatic work for a process is a function of end state only. This indicates that the adiabatic work is a derived property. Remember that if the properties depends only on the state. So, if adiabatic work, which we are saying is basically a function of end state, then essentially this is a derived property. We can say this to be E. In other words, we can say that, well, the difference in this E for the case of adiabatic process would be simply W A 1 to 2. This is a representative of adiabatic work between 1 and 2, leading to between 1 and 2, which will be difference in this derived property, which because it just simply depends on the state, and this E is nothing but of course total energy. Okay. Now, most of the cases we are going to ignore the external force, initial force, hence the total energy can be reduced to internal energy, which is nothing but which relates to the molecular motion, intermolecular effects and intermolecular interactions, which we all know. Okay. Now, earlier we have also mentioned that U could be a function of this. This is something which we are aware of earlier in our lecture week 1 discussion we have gone through. as well as we know that is also first order in the total mass. Essentially the order is given here, that if you consider u to be a times m1 to so forth, it will be simply a times u of this. That we know that extensive property of the energy. So now we connect all these things. So essentially the missing work for any process, okay, whether it's adiabatic or non-adiabatic, would be nothing but heat. So for the case of adiabatic one, this is going to be 0 as we have already defined, okay. But in case of a non-adiabatic, you are doing additional work, or that will be your missing work, and the difference is basically nothing but this. So this is what the definition of the heat is, nothing but the property here, E final minus E initial minus the work which you are doing it, and this of course leads to the first law. So this is the sign convention which we already have discussed. Okay, so I quickly go through this heat interaction, the last few slides here. So this is the simple system which we are considering a system, composite system A and B separated by diathermal wall. So the only type of interactions that can occur between A and B is basically heat interaction, because this is a diathermal, only the heat can flow, and essentially there will be no work because this is rigid. So you have delta EA is equal to minus delta EB based on the energy conservation, which is what this is, and the corresponding QA is basically minus QB. Okay. So what we are saying is that this when the interaction ceases, after some time the composite system will be at equilibrium. That is a fourth postulate 2, and that is what we are trying to say, that once the system must tend towards equilibrium state and interaction must eventually cease. In that case the system would be considered as thermal equilibrium. So that is another way of putting things, making use of this properties or the postulates. Okay. And that leads to our final postulate here, that if the sets of system A, B and AC each have no heat interactions when connected across non-adiabatic walls, there will be no heat interaction if system B and C are also connected. So that means if A and B are at thermal equilibrium and A and C are at thermal equilibrium, then B and C has to be at thermal equilibrium. This is what we know as 0th law of thermodynamics. Okay. And this also can be considered in the form of thermometric temperature. So this postulate can rank the thermometric temperature. So if we say that delta EA is equal to minus delta EB, which is less than 0, or equivalently QA is equal to minus QB, which is less than 0, then essentially the temperature of A should be greater than temperature B. This you can consider from that composite system here. Okay. So if there is a heat transfer from A to B, and since based on the convention, if heat is transferred here, the heat is going to be negative, the corresponding temperature has to be more than of A will be more than of that of B. That is what basically is this statement is saying. Okay. So in other words, for pure heat interaction, there must be a temperature difference between system A and B. I believe that what this lecture we wanted to do is to re-emphasize the set of understanding which we have created in the first week, but in a different form, and to illustrate that the similar things you can do in a different way, to come to the first law of thermodynamics. In the next lecture, we are going to do is we will focus on basic examples of the open systems and closed systems, and hopefully that will give you or refresh your memories of the engineering thermodynamics before we head to more complicated aspect of chemical engineering thermodynamics. So I will see you next time.